our 6G networks, use
Fantastic.
cases and technologies.
It's very good. Okay, I managed to install my webcam as well. So Marco, hi.
Hi. Okay. Now we can.
Yeah.
see each
Well,
other.
thank you, and thank you, Leonardo, for stepping in with these roles of speaker and moderator. And it's a really nice thing to see. We are being connected through IEEE.
Okay. Great.
Very good.
So is this presentation going to be streamed here on the WebEx application?
We have separate software that we are using. It's a little bit more professional software for broadcasting.
Oh, okay, okay. Because I see here that we have one attendee.
Yeah, yeah. No, don't worry.
Okay, okay.
Even at the end, we have 200 to 400 people who watch the video.
Okay.
It's that's an average. For these technical topics, that would be a pretty good estimate of what you can expect.
I see.
And yeah.
I've never used this dual software before, so I don't know actually how it works.
It's the only, I mean, people are too lazy to find a connection thing, to join the WebEx. But if you're watching the stream, it's easier. You can do something else while you're listening to it.
Yes, of course. I can put the mute.
Hello everyone, my name is Leonardo Benito de Souza. I am a master student in power electronics at Federal University of Santa Catarina, Brazil. And today we have Marco Giordani. Marco Giordani is a professor in Department of Information Engineering, University of Padova, Italy. And he's presenting a presentation entitled as Tower C6G Networks, Use Cases and Technologies. Welcome, Marco, and thank you for your presence.
Thank you, Leonardo, for the introduction, and good morning or afternoon, wherever you are, and thanks for attending the presentation. So, as Leonardo said, this presentation will be about 6G network and a presentation of use cases and possible technology. Before we start, let's give a brief introduction about where I am located. So I am in Padova. That's a city in the northern part of Italy, very close to Venice. Padova is the second oldest university the University of Padova is the second oldest university in the world and is consistently ranked among the best ones in Italy according to the quality of the education. We have been some notable faculties and students in the past, so I am very proud of sharing the history of my university. As far as I am concerned, I am part of the Signet research group that focuses on several different fields in the area of networks and communications, as you can see from this slide here. The Signet group includes several students, faculty members, and engineers. And what I will discuss about today is in the area of 5G networks, where we've been pretty active in the past. And also, we are looking at how the 6G network is evolving towards, the 5G network is evolving towards 6G. And this will be the main focus of my presentation. So let me start briefly by discussing how we went from 1G in the 80s up to a completely new wireless generation for networks, that is the 6th generation. So how we got to 6G. We can say that every generation of mobile technology has tried to address the requirements and the needs of the network operators as well as the society. And now we are moving towards the 2030 era, where there will be new use cases and new challenges that needs to be supported with more advanced technological solutions. And that's why the research community and the standardization bodies are looking towards a 6th generation of wireless network, which is called 6G indeed. And this might look pretty weird that we are discussing about 6G now, when we should say that 5G has already started its official rollout. So you may know that a few weeks ago, Apple released the first ever 5G iPhone, and in Italy, but I'm sure also everywhere in the world, the telecom operators are advertising 5G plans for the smartphones. So we know that even though the 5G that is currently being released might not look like the 5G NR standard that was developed by 3GPP in the past, it's obvious that the 5G commercial rollout has already started and will dominate the market for
many years to come. So the question is, why are we talking about 6G right now? It might seem very ambitious to discuss about that, but actually, historically, every generation of mobile network appeared approximately every 10 years. And the first release for 5G for the standard was in 2018. And this is the actual year when the first commercial rollout has begun. So we reasonably expect that 6G will actually release within the next 10 years, so around 2030. And that means that this is actually the right time for the research part of the things to start. So we need, from these very moments, to identify the future communication needs, the performance requirements of the applications, the system and radio challenges, and the major technical options in the context of 6G. So we can say that the time is pretty right. So now we should talk about why we need to go beyond 5G. So why we should discuss about 6G in this time frame. Well, as it happened for the previous generations, the discussion cannot be done without looking at what happened in 5G. So in the same way that 5G requirements and technologies, well, were derived from previous generations, including based on LTE shortcomings, in the same way, we expect 6G innovations to build upon the leftovers of 5G. So on one side, we'll redefine 5G applications requirements that we don't expect will be satisfied within the 5G timeframe. And at the same time, we accommodate completely new use cases that have not been imagined today, but that will probably be part of the 2030 society. And the same goes for the technological solutions. Some solutions cannot be developed within the 10-year time frame of 5G because of markets not ready yet to support them, or simply because we don't have the technological innovations that are needed. And at the same time, we will introduce completely new connectivity solutions that will be shaped according to new players that will come to the market in the 2030 era and beyond. And most importantly, 6G discussion will try to overcome 5G limitations that have not been thoroughly investigated, both in the research and by the telecom operators, like providing connectivity to rural areas where most of the population is not even getting access to the internet, providing and ensuring public safety everywhere, every time, thus increasing the robustness and the resilience of the network, and also providing a more environmental clean energy from the energy perspective environment. Also, the role of the upload was relegated to the very bottom in favor of the downlink, and also how to manage and optimize the network has not been investigated yet. So in support of what I'm saying, you can see from this slide here that the standard is also looking towards 6G. So it's not just the research community or university in this sense. The 3GPP has started some study items for a new 6G specification, and also ITU is looking towards the requirements and the use cases that 6G will need to support. And the companies are also looking towards definition and development of proof of concepts and test beds that can show the actual benefit and the power of a new wireless generation. So what I will discuss in this presentation is giving out the use cases that are envisioned for 6G, presenting the requirements and the KPIs that these applications will need to satisfy, and based on this, present the technologies that can make it possible for these very challenging requirements to be satisfied. And I will provide a full stack end-to-end perspective. meaning that we'll consider all the layers of the protocol stack to be modified for 6G, from the physical layer to the higher layers, including new network architectures and deployment strategies. So in this presentation, I will not provide equations or numbers. I will try to keep it high level in order to present the concepts that will be more important in 6G. As much as possible according to the time I have. And the idea is to provide guidelines on the most promising research topics in this field and stimulate further work on the 6G concept, whose research has just started. So let's start with the use cases as promised, and then we'll go into technologies. So here is a list of possible use cases that have been considered for 6G. As you see here from this slide, some can look very similar to 5G-like use cases, even though you'll see that there are some differences, in particular in the requirements, while some other use cases are completely different and will address the characteristics of the networks in 10 years from now. So the first I want to focus on is industry and manufacturing. That's the digital transformation towards a new revolution of the industry, towards Industry 4.0. And in particular, what we have to satisfy is the need for ultra-reliable, low-latency communication for activities like exploration or mining, or even monitoring of pipelines. And what we have to comply with is make robots cooperative. So make it possible for a set of robots to accomplish a task that a single robot cannot perform itself. And on one side, we need to guarantee intra-machine communication, like replacing physical cables with wireless infrastructures, like operating at terahertz or with new semiconductor technologies and innovations. But the most critical part will be inter-machine communication. So communicating among different machines that might be very far from each other. This has to be done by keeping latency very low and providing high reliability. One way to do that is by integrating multiple radio access technologies together, as it is partially done in 5G, even though in this case, the requirements of latency and reliability that are typical of the industrial applications are still needed to be discussed. And this is why 6G will try to address these characteristics. Another use case is teleporting. This is very new as a concept. It's the actual delivery of a holographic experience of a certain object in real time without any handset technology. So it's very different with respect to virtual reality or augmented reality, where you have to put something on your face in order to fully experience the virtual world. This will be very important, especially in these very difficult times where we have to make all our everyday activities virtually. By making it possible to have a real digital experience, we can not only improve the labor productivity and in order to allow better interaction during business events, for instance, or working events, but we can also decrease the time and the energy that is used for traveling. So it's going to be very, very challenging as a use case. Also because 5G and previous generations have typically been designed to support audio streaming or two-dimensional video streaming. While now we have the issue of sending non-physical human senses, including smell and taste, which is particularly challenging. And also while 5G typically broadcasts regardless of the viewer's position, now when we are into the field of holographic, we need to add the parallax. So the image will change depending on the viewer's position and the interaction of the viewer with respect to the object. So you see that for these applications, the data rate requirements are going to be massive. We are talking about terabits per second. which is orders of magnitude more than what 5G is expected to provide. And at the same time, latency has to be kept very low to allow for a smooth and immersive holographic experience on its own. And very much related to teleporting, we have digital twin, which is a concept very much associated with VR and AR. It's creating a digital replica of a certain object having the same characteristics of the real device, of the real object. This is very important. It is particularly important in the industry domain because we can allow multiple teams that are in various different remote locations to work on the same three-dimensional shared representation of the object, thus enabling better simulations of the product behavior and better maintenance of the different systems. And the main concern here is how to make it possible for the different replica, for the twins, to be synchronized. And the synchronization here means that the rate at which the different objects are transmitted is going to be increased by several orders of magnitude with respect to 5G. So this is another very challenging concept to be discussed about. And then we have the field of smart transportation. Smart transportation, like autonomous driving, is something that has been discussed in the past for 5G, for example, but I'm sure that we can all agree that it's going to be very difficult to see fully autonomous cars on our roads within the next 10 years. We are expecting some more automatic behavior, but still we need to wait a little bit more to have a fully autonomous framework. So this is naturally going to lean towards the use cases supported by 6G. And this is not only for the infotainment part of the framework, so providing like virtual reality services to the passengers or the drivers when they will not need to drive anymore, but we are also discussing about making it possible for vehicles to communicate to each other and share their sensory observations around, thus fully exploiting the potential of the autonomy in the system. The key challenges here are, well, first of all, the need to share all these sensory data in a very timely and continuous way, which requires terabytes per driving hours, according to some estimates. And the main limitation here is the reliability that needs to be satisfied. Of course, there will be catastrophic consequences in case of communication failures. So we must guarantee that the probability of failure is very, very close to zero to make it possible to have a safe environment where cars will move. And this is something that 5G, with the technologies that 5G has released so far, will not be probably accomplished. Another issue is public safety. So how to deliver information at very high throughput throughout the chain of command during natural disasters or some other very bad situations that may arise in a certain incident area. Current public safety communication is focusing on voice or sending, while instead sending data is going to be more critical. And the three-dimensional rendering of the environment that can be provided by AR and VR technologies, as well as the holographic telepresence, will require very high data rates to be supported. But the most important constraint here is in the latency. The latency has to be kept very small. And we're talking about the end-to-end latency. So not only the latency in the radio part. So there is the evident constraint of the physical world. So we cannot go faster than light, and this is a given. But still within reach, we need to develop solutions that can push the over-the-air latency requirement as low as possible, possibly in the sub-milliseconds region. And there are some technological solutions that can be developed in order to make it fully possible to achieve this goal. Health and well-being will also be another area where 6G will do and provide enhancements. We are talking about the evolution of healthcare to support telemedicine, as well as healthcare workflow optimization. And one concept that is very important in this period in particular is transitioning towards a care outside the hospital paradigm. So providing the care services directly in the patient's home. And this allows not only individualized and personalized assistance, but can also reduce the costs for the healthcare and will make it possible for healthcare to be provided to those people that have limited mobility or that live in underprivileged areas where there are simply no health facilities ready to host them. The current major limitation here is the lack of real-time feedback that needs to be supported. And when we provide this health paradigm through VR, AR, or holographic communication, then we also have very strict requirements in terms of throughput and latency to be satisfied. So this is another area where discussion is needed. We also have the IoT world that is important in 6G. In 5G, IoT has been limited to the smart city revolution, so sensors and wearables deployed all over the city to make it more efficient for the city to be managed. In 6G, we are doing more, so not only related to cities, but also other types of areas where automation will be key, like agriculture and farming, as well as warehouse management, and everything that is related to the industrial domain, like the possibility to have better coordination between industrial machines and robots. The requirement here is to go towards a zero energy device, which is something that 5G is currently not supporting, and that will need more attention. And I want to conclude this part with another topic that 5G so far did not address properly, and this is the financial world. Everything is related to the banking environment. In particular, high-frequency trading, a method of trading where there are some computers that can transact millions and millions of financial decisions in a fraction of a second. And since just a single second can have a very big impact in the trading efficiency, you can see that it's very important to make it to reduce the latency as much as possible to allow for more efficient transactions. And then the blockchain technology has also gained momentum in the banking industry as a solution to decentralize or even eliminate some financial intermediaries. And we can also guarantee improved transparency and security, like using the quantum computation. And so reliability is something that 6G will need to go and look through. We are envisioning a 100% improvement in reliability in 6G with respect to what 5G was able to provide. So as you can see from this slide here, we are trying to envision the KPIs for 6G. So these have not been officially defined yet by ITU or some other organizations, but still we can draw some guidelines, like the density of devices that will be needed to provide connectivity to will increase by at least 10 times with respect to 5G. So we are hitting the 10 million devices per square kilometer to be connected at the same time to the network, which is quite a lot. And also, as I mentioned before, latency will be reduced in the sub-millisecond time frame, as well as data rates will hit the terabits per second requirement. And these KPIs will not probably be supported in 5G. And we need new technological solutions that make it possible for these very demanding requirements to be fully satisfied. And this is where the research is going through, and this is what I will discuss about in the second part of my presentation. So let's see new technological solutions that have been and will be enabled by 6G. So let's move a little bit, let's make a step back and review what 5G introduced in the latest standards. So 5G introduced a completely new flexible frame structure. It introduced virtualization and softwareization in the network, going into a very lean core network design. It introduced the concept of massive MIMO to realize spatial diversity and beamforming. And it also introduced new spectrum solutions. First and foremost, the use of the millimeter wave technology in networks. So let's start from new spectrum solutions, and let's see whether 6G will also move in this direction and provide new connectivity innovations in this sense. So since 5G provided the evolution from the legacy spectrum into the millimeter wave spectrum to benefit from the very large bandwidth that can be available in the high frequency domain, what we ask ourselves is whether 6G can go even higher in frequency. And the answer is yes. So what 6G is actually looking through is going into the terahertz bands, which is much more than millimeter waves, and even leaving the RF domain and going to the optical domain, so using visible light to not only illuminate a certain area, but also providing communication. So let's start with the terahertz communication. The terahertz bands operate roughly between 100 gigahertz and 10 terahertz, more or less. And compared to millimeter waves, we can finally bring to the extreme the potential of high frequency connectivity, enabling data rates in the order of hundreds of gigabits per second. So in line with the boldest requirements of 6G applications. There are some issues to be faced though. The first one is the very large propagation loss that is experienced when we go higher in frequency. Even though these can be partially overcome by using directional antenna arrays, as it is done in 5G with MIMO, still we need to see whether antennas in the terahertz spectrum can be designed. It's going to be very challenging, both from an engineering point of view as well as from an economic perspective, because this is going to be very expensive for the operators and the industries to be built. At the same time, there are some bands that will be severely affected by molecular absorption when we go higher in frequency. And these bands have to be carefully identified and avoided when we have to transmit. So the bottom line here is that terahertz is possible if we operate at very short distance, like within the machines. So to provide inter-machine communication, intra-machine communications, or if we are in the outer space, like for satellite, inter-satellite communications. But the important thing is whether we can use terahertz to communicate also at a larger distance. And this is something that should be investigated carefully in the research that is going to be conducted in the 6G domain. Of course, we can go higher in frequency, and we can go even beyond the terahertz, so going into the range of the visible light. There are several advantages when we go into VLC to communicate. One is that we don't need to spend money to design very complex RF equipment operating at the bandwidth of terahertz. because we can simply use cheap LEDs to not only illuminate, but also to send data. So by simply modulating the intensity of the signal, we can design and realize a proper receiver for the data. And also by using LEDs, we can operate through very narrow beams. So we can concentrate the power in a very tiny portion of a very geographical, small portion of the space, thus increasing the link budget. And because of these very cheap devices that can be used for VLC, the research on VLC is much more mature than what terahertz is, since, by the way, the IEEE has already defined a standard for VLC. VLC also suffers from several issues. The most important one is the issue of interference. Interference from light, from other illumination sources like lamps in an indoor environment, or the sunlight if we operate outdoor. So even here, there are these very critical challenges to be faced. And the common understanding here is that we can use VLC if it's complemented by an RF counterpart in the uplink. So the best scenario for application of VLC is the indoor environment where there is very limited sunlight, or even for vehicular communications by night, because we can use the taillights of cars to send signals. So when the car brakes, we can use the taillights and VLC to inform the other vehicles around about the braking decision, and then autonomous decisions for driving patterns can be made accordingly. So these are the two most important domains in this research domains in the area of spectrum technologies that 6G is looking at. Now, besides new spectrum, 6G will also transform the wireless networks by introducing new technologies that will operate from the physical layer to the network architecture that are not yet part of 5G. And I've categorized them into the disruptive technology domain. And the first one is full duplex communications. Full duplex communication means that the transceivers are able to receive a signal while also transmitting. I have to say, full duplex has been discussed for decades in the past. And also in the 5G context, we have seen some papers and devices promoting full duplex communications, even though it did never see the light due to very big technical difficulties, the first one being the self-interference issue. So what 6G will do within the technological innovations is to design new antenna and circuits that can reduce the crosstalk between the transmitter and the receiver circuits into a specific device. So the goal will be to enable concurrent downlink and uplink transmissions to increase the multiplexing capabilities of the systems without, and so the throughput, without additional bandwidth. So if full duplex is designed correctly, we may even avoid using the terahertz bands that have all these challenges I've described before, and we can simply increase the throughput with the same bandwidth. And the most important part of the research will be dedicated to the design of new scheduling mechanisms to determine the appropriate combination of downlink and uplink resources and the corresponding powers and rates to be used to maximize the network performance. And this is very important because the role of the uplink is gaining more and more momentum with respect to downlink, as it is, since right now the traffic is unbalanced towards downlink, but in the future we are expecting to see even more uplink than downlink in future networks. So the need of maintaining at the same time uplink and downlink transmissions through full duplex communication is something very important that deserves further investigation in in the research. Another issue is the so-called out-of-band estimation, which is referred to the concept of channel estimation. So when we operate at high frequency, like at millimeter waves or in the terahertz domain, we need to make channel estimation. So to decide if we operate through directional transmissions, which is the optimal direction where to send the signals. And channel estimation in the high frequency spectra is very challenging. First, because we need to operate through very large bandwidths. So we have a lot of bands to span to make the channel estimation, which can be timely, which can take a very large amount of time until we find the optimal configuration. And also at high frequency, the channel varies a lot over time. And so once we estimate the channel and when it's actually time for transmission, the channel can be completely different. And so we have to re-estimate the channel all over again. And this is not efficient at all. So the idea that has been proposed in the past is to make channel estimation in terms of angle of arrival and departure out of band. For instance, in the legacy spectrum, in the sub-6 gigahertz spectrum, where everything is better, where propagation conditions are good. And then define a certain transformation functions that can convert what we estimated in one frequency domain into a much different frequency. This is not easy. The transformation function is not easy to be found, but we can leverage some information about how the channel, the high frequency channel is structured. In particular, the high frequency channel is sparse. So we can exploit compressive sensing mechanisms that can estimate the channel with a very reduced number of samples. Like in the figure here on the center of the slide, you can see that it's clear that we can identify 6 dominant paths in the environment. And each of these squares reflects a certain angle of arrival and time delay for a single path. So by simply looking at these specific regions of the channel, we can estimate it in the sub-6 gigahertz domain and then convert them into millimeter waves. So this is something that should also be investigated in the future, and this research started in 5G and will continue also in 6G in the future. There is also the issue of providing good accuracy for localization. In 6G, we are expecting a very sub-centimeter localization accuracy, both outdoor and indoor. And this is very challenging, especially when we use GPS. GPS works under clear sky conditions, but if you are in a urban canyon or in an indoor scenario, you cannot use geolocalization at all. Like in the indoor case, for providing public safety services, you need to locate a person that is trapped inside a skyscraper in an emergency situation. How can you tell where the person is, since the indoor scenario cannot be reached by geolocalization? So the solution here is to use RF signals to enable not only localization, but also sensing and communication. And this localization can be practically improved when we operate at high frequency. Because by estimating the map of the environment and projecting the time of arrival and the angle of arrival information, we can estimate the user's position. And as long as we increase the frequency, so we decrease the wavelength of the signal, we can improve the precision of the estimation for the position. And that's why, compared to millimeter wave-like localization techniques that were developed in 5G, the use of terahertz and also VLC in the indoor scenario can make it possible for the localization accuracy to be improved a lot. And so this is something that should deserve further investigation as well. So right now we've seen the communication technologies, the new spectrum, and also something that is more physical layer related. We also need to change the whole network architecture, because simply 5G requirements are different from what 6G once will be like. For example, if we operate at terahertz and we provide terabits per second of throughputs, then the demands on the transport network, on the backhaul network, is going to be very intense. The core network itself will be more stressed, and today's implementation will probably not be able to efficiently support these huge traffic requests. And at the same time, we expect different communication technologies to be used simultaneously, like millimeter waves, terahertz, VLC, and also the legacy technologies. And this will increase the heterogeneity of the network, which will also need to be managed. So let's see how the network architecture can be improved when we design 6G technologies. So one is the use of SDN. So yes, SDN, virtualization, disaggregation of the networks are concepts that were already discussed for 5G. But there are so many issues that 5G has not been able to solve yet, like, for example, how to design an architecture that is able to satisfy the very strict latency requirement of 6G applications in a centralized way, or security, how to provide security when the network is fully converted into something that's virtual, which can be subject to cyber attacks. So all these questions have to be solved when we operate at in 6G. And one option is to make fully exploit the decoupling of the control and the data planes, thus making the network programmable and replacing hardware with software. This also allows for better centralization and control of the network, which is vital when we make the devices sharing data among themselves. And having the data available for a network is fundamental if we want to make network functions as much automatic as possible. We don't want the external manual intervention anymore. The network has to be as automatic as possible in order to reduce the latency and improve the reliability on its own. So having a central controller like SDN can support can make it possible for data to be aggregated and for better decisions to be made. And this is the concept that SDN is going to support and provide. And another very important concept is the centralized RAN technology. So to increase the centrality of the network by splitting the network functions into one centralized unit and several decentralized units that operate towards the central one. This can not only reduce the cost for the deployment, but also promote better energy saving functionalities, because the DUs, the decentralized units, can just implement a subset of the base station functions, where we delegate all the most expensive from a computational point of view actions just for the CU that manages all other networks. This is something that has some challenges that still need to be addressed, like what's the optimal degree of centralization that we can provide. So how many DUs can a CU actually support? The most important constraint is in the backhaul part of the network, because if we have too many DUs, then they may overwhelm the backhaul link at the CU part, and this will at the end of the day, decrease the overall performance of the network. So the design of the C-RAN has to be thought very carefully, and that's why further research is needed in this domain too. What we are going through then is towards a cell-less architecture. So an area where we remove completely the concept of a cell boundary. So we don't want the user to be connected to a certain cell, but we want the user to be connected to the network on its own. In this way, we completely remove the need for handovers that are particularly challenging when we operate at high speed or when we operate through very high frequency spectra, which imply that the link that can be achieved between a base station and the user is very small. If we remove the boundaries of the cell, we also remove the need for overhead and for the control part of the signals to be shared when the handover has to be triggered. So cell-less architecture is something that should be discussed, especially when multiple technologies coexist at the same time in the user. So what we have to do is to provide the possibility to transition among the different heterogeneous links that can be established without manual intervention or configuration. The idea is that according to the specific use case that we want to provide, or according to the requirements of the network, then we decide which technologies to use and which can complement each other's limitations. Like one possibility is to use the sub-6 gigahertz spectrum for the control plane, and then boost the capacity of the network by transitioning towards terahertz in the data plane. And this also goes into the direction that I mentioned before of SDN, where we can split the control plane and the data plane and make them operate through different interfaces and different technologies at the same time. Now, another very important part is providing rural connectivity. This is a very big issue in 5G, and I want to stress this concept once more because I think it's going to be one very hot research area in the future. So in 5G, we discuss about high capacity, low latency, high reliability, but all these connectivity requirements are typically provided in the urban environment, where connectivity is already there. And the reason is that the urban environment is where telecommunication vendors and network operators will benefit the most from the 5G rollout. So the research community so far completely ignored or relegated to the very bottom the issue of providing connectivity to the rural areas. Just think that around 1/3 of the population in the world has no broadband access connectivity. And this is something that sooner or later will have to be taken care of by the research community and by the standard. One possibility is to deploy base stations in those underprivileged areas where internet is not provided so far. But this is not feasible most of the times because, well, on one side, will further increase the energy consumption of the ICT systems, which is already a significant part of the overall carbon emissions in the world. Second of all, because sometimes it can be very difficult to install base stations in some areas, like over the ocean or in the desert. And even if we did provide new infrastructures for providing connectivity in the rural areas, then we will still be open to possible external attacks, like terrorist attacks or natural disasters, which may make unavailable anymore the terrestrial infrastructures. So one other area of research of 6G is providing the so-called Internet of Everyone connectivity. So connectivity that is intended to everyone and that continues every time and everywhere in the world. And one way to accomplish this is by shifting from a 2D-like network paradigm into a three-dimensional network architecture. So to support terrestrial infrastructures with non-terrestrial elements, like drones or satellites, that can supervise the network behavior from the top and provide additional functionalities to improve the capacity of the system. So on one side, the non-terrestrial elements can be deployed where it's needed immediately. They can be deployed on demand, like we can deploy a UAV in a certain area where there is an emergency and there is no public infrastructure available. Or we can even use these non-terrestrial elements to provide additional degree of freedom to increase the robustness of the system. These elements can also be used as an access point for the backhaul part if the actual fiber-like backhaul systems are overwhelmed. So there is a very good approach here to be made. And we also conducted some simulations to check whether we can use these high-frequency bands to communicate also from the non-terrestrial part of the network, like from satellites. The challenge is evident, right? The challenge is that we have huge length to be traversed. Like from the satellites, we have thousands of kilometers that the signal has to go through. And the path loss is going to be very large when we operate at high frequency. But if we design antenna arrays properly, or if we make multiple layers in the non-terrestrial domain cooperate together, like using a high altitude platform to bridge the signal that comes from the satellite towards the ground, so amplifying the signal, then we demonstrated that it's actually possible to use millimeter waves, for example, to provide internet connectivity on the ground by using satellites or other non-terrestrial devices. So this is a concept which is 6G specific. It was not all included into the first preliminary 5G standardization specifications. So this is going to be one very critical area of research as far as 6G is concerned. And as I mentioned before, non-terrestrial nodes can be used also to provide backhaul assistance to the terrestrial networks. And the reason is that when we consider very dense deployments, we have several issues to be addressed. In particular, the fact that every base station that we deploy has to have a fiber connection to the core network to deal with the backhaul traffic. And the more base stations, the more expensive is going to be the deployment. So one solution that has been envisioned in the research community is to move towards the so-called integrated access and backhaul paradigm. So to replace a certain link for the backhaul from wired fiber-like connection into something that's wireless. So realizing wireless backhaul links and using the same frequency spectrum to provide at the same time access connectivity to the users, and then to relay their backhaul traffic to the core network. So this is a very powerful idea, and in fact, there are already some very promising results demonstrating how we can reduce the deployment costs of the network as well as satisfying the capacity requirements of the systems. And this concept can be fully exploited when we operate at 6G. When we use, for example, terahertz with very large bandwidth to provide at the same time just splitting the bandwidth, both backhaul and access connections. Even though there are some issues still to be addressed, as I was saying, like what is the maximum number of wireless backhaul nodes that we can deploy out there? Eventually, the backhaul traffic will need to pass through a certain fiber connections to get to the core network. So if there are too many of these wireless IAB nodes to forward the traffic to the core network over the fiber provided by a certain base station, the backhaul link will be overwhelmed. So this is something that has not been addressed yet. The research has just started investigating this area, and that's why in our research department we have developed an NS-free module for IAB at millimeter waves, which is open source, and you can easily download it for free at this link. And by installing the simulator and the module for IAB, you can actually see where the issues are, and you can also decide which are the countermeasures to take or design, implement, or propose possible solutions that can solve these issues that are so important right now. I want to conclude with discussing about intelligence and providing a fully intelligent network design in the future wireless systems. The fact is that, yes, we are seeing more intelligent networks in 5G, even though the main tasks are towards classification and prediction of the systems. But we expect the 6G intelligence to play a much more prominent role in the network, because we want to transition towards a full stack end-to-end optimization where the network will be fully autonomous and will make decisions independently on the central control of a central node. So let's see, and let's review the most important innovations that are being discussed in this domain. For example, you can see here that there are several parts of the networks that will benefit the most from intelligence, from artificial intelligence to be provided, like how to solve the trade-off between latency and reliability that currently affects the network, or how to improve the perception of the systems, of the objects, to improve the recognition and the control plans. So different areas in the wireless networks will benefit by intelligence and by machine learning in particular. And machine learning in the 5G domain, it was typically, so the 5G, the machine learning mechanisms that were discussed for 5G were specifically supervised learning and unsupervised learning. The second one even more than the first, because we can also use it without the need to have labeling in the first place, which can be unfeasible when the number of devices or the traffic, the data is going to be increased. And also, when we go into 6G, the reinforcement learning part is also making a step forward, in particular because we have the possibility to exploit the feedback that arrives from the receivers and then change our transmission patterns accordingly. But there is an area that will be the most important one in 6G that has not been considered currently, and that's distributed learning. So distributing machine learning workload across multiple machines. So turning from a centralized into a distributed system. And in this case, federated learning is one of the most critical examples of this paradigm. With federated learning, we do not have to share raw data, which can overwhelm the channel and which can be pretty difficult to be provided. But we can just share models of the environment, like a certain, if we detect a certain anomaly, or if we can predict the behavior of the network in a future time instant, and so on. So we operate locally, and when our model changes, we send the upload to the central entity, to the central server, which will then make more efficient decisions based on the updates that are delivered. So not only this approach provides more personalized learning, because we can use our own data to make our own decisions locally. But also what we can guarantee is security of the data and privacy, because we don't send the data anymore. We keep the data for ourselves, and we just send the updates and the model that we have processed on board. And as I was saying at the beginning of the presentation, the security part of the network, the privacy part, was something that 5G did not look carefully into. And the use of distributed and federated learning for 6G is something that can really make a difference in this domain. And data is going to be vital for networks anyway. And so what we can do is to make use of the data in order to select the pieces of data which will be more valuable for the network. So if we cannot send data because sending too much data will overwhelm the network resources, what we can do is to select the data which will be more valuable for the receivers by answering these questions. So which data do we really want to transmit, when it's the optimal time to send them, and which technology should we use to make the data broadcasting. And what we can do, for example, is to decide how we can compress efficiently, especially when we are in an autonomous driving framework where we have a lot of sensors with different characteristics to be considered. Like the cameras provide a two-dimensional representation of the environment, while some more sophisticated sensors like the LiDARs provide a three-dimensional point cloud of the environment. So how to compress this new type of data efficiently is something that should be really investigated. And also we can look at the nature of the data before sending it. So if we see that the data is very correlated, because we are on a highway and we don't see anything but the background, then by accessing the data or by evaluating the utility that the certain data had for the receiver, we can discriminate the utility of the different pieces of information and decide which one should be prioritized in the transmission. The question here is where in the network, in which part of the network, this processing should be done. Should we do these decisions on board of a vehicle, for example? The issue here is that the vehicles typically don't have very powerful computational facilities. So the decision delay can be very large. So one other approach is to send and to deliver the burden of making processing of the data in a distributed, decentralized edge cloud, for instance, where we have very strong computational capabilities, which can reduce to almost zero the decision time. But the drawback is that we need the latency for transmitting this data and also for the feedback to be sent back to the device. So this is a very important question that is still open. Where should we install the machine learning algorithms, and where the intelligence should be placed is something that should be carefully investigated in the future. So to summarize, let's say that we have seen that there are several areas where 6G research can investigate. We have everything that is related to the spectrum part, both from the circuit part of the research, as well as something that regards the communication part. And then we need to change all the layers of the protocol stack to make it possible for the 6G use cases to be satisfied, from the physical layer to the higher layers up to the architecture. And that's why the research on 6G is going to be so difficult and at the same time stimulating in the next few years. And I want to conclude with let's say something that is new with respect to what we have seen before. something that, for instance, in 5G, we did not see really. It's the new fight that is going to be held between the telecommunication operators and the telecommunication vendors. Because from one side, since we have all these new challenges to be faced in 6G, we have new technologies to be discovered, to be designed, to be implemented, and finally to be patented and sold. And this is a very good part of what telecommunication vendors want to do. At the same time, the telecommunication vendors are willing to go into the 6G domain to have better possibilities and opportunities for creating new products and technologies. But at the same time, the telecommunication operators invested billions and billions of dollars in the 5G technologies. They also bought the 5G bands, and so they want to fully exploit the 5G services that they just started to release and roll out. So for the first time, probably, the interests of the operators and the vendors are diverging. They're not the same anymore. So I guess we are going to see a new scenario where the two types of players in the telecommunication world are going to fight and to pursue different objectives. And with this last comment, I will stop here. I will conclude my presentation, and thank you again for your for listening to the presentation and for attending this event. Thank you.
Thank you, Professor Marco Giordani. Now we have a Q&A section of approximately 20 minutes. Is that good for you?
Of course.
Let me see if we have questions here in Q&A section. For the moment, we don't have Q&A. We don't have questions yet. They ask me if these slides are available somewhere. This presentation is being recorded and being broadcast in Facebook page of IEEE Young Professionals Region 8. So in the YouTube channel of the IEEE Young Professional Region 8, you should be able to find the video afterwards. And this presentation is being broadcasted. So we don't have questions so far. Let me see. Professor Marco, can we wait for more?
Sure,
2
of
minutes?
course, I can wait, no problem.
And if no one make questions.
Hi, Marco. Can I ask you a question from my part?
Of course.
So, okay, it's a little bit wide just to start the discussion. So what do you think, how much is the implementation of 5G rushed, or is it just in time? Is it appropriate? Is it mature technology, or should we improve it a little bit more and be patient to add all those characteristics that you were talking about?
Well, thanks for your question. So in my opinion, the research on 5G will have necessarily to improve in the next few years. And this is something that it's pretty in line with what happened in the past. So the first specifications for 5G have been released, but the first commercial rollout of 5G is not, it's not exactly like the standard, because the technology is not ready yet to support these innovations. So the research is going to be much faster than the actual final deployment of the commercial devices. So for having a really standard compliant 5G technology in the commercial products, we might need to wait some more time. But we are going into the right directions, I'd say. What 6G is going to provide is something that 5G will not probably provide within the time frame of 10 years from now, because the markets will not be ready yet to support these innovations, or simply because the times are not mature yet. So yes, there will be some enhancements of 5G technologies, but in this case, we are targeting completely new, different paradigms that won't probably be included in the later, in the future 5G standard specifications.
Professor Marco, I have a question. Regarding, I've seen in the picture that 6G, the idea of 6G is using non-terrestrial networks as well. So in the project of Starlink, is this the idea as well? Is the project Starlink using ideas of 6G networks, or it's another technology?
Yes, so actually what Starlink does is to launch a very large number of satellites in the LEO orbit, so in the low Earth orbit, to provide access connectivity on the ground, which is in line with what I mean by non-terrestrial networks. The reason why Starlink is launching so many satellites is because when you are in the low orbit, the angular velocity is very fast, so the satellites will be very fast moving with respect to the users on the ground. So you need a wide set of satellites, very dense constellations, to provide continuous connectivity. If I am not wrong, there should be more than 12,000 satellites deployed in the complete framework for Starlink. So this is something, but the research will solve even more issues, like making it possible to fully exploit the coordination among different layers of the non-terrestrial domain. So not only using satellites, but complementing satellites with other nodes that fly over the air, like the UAVs, the drones, or the high altitude platforms, or the aerostatic balloons. If we fully exploit the potential of a multi-layered network, then we can solve these issues that are typically associated with the standalone terrestrial deployment, as Starlink will going to be like. But yes, the concept is very similar, providing connectivity, internet connectivity everywhere in the world, not only where we can actually install physical terrestrial infrastructures like in the urban environments.
Thank you, Professor. I will make another question, Professor Marco. In rural areas of Brazil, most part of in Amazon region, those regions, they are not covered by 4G or 3G network. and research in
sorry, I'm actually losing you. We are experiencing connectivity issues in this very moment, this very same moment. So can you repeat, please?
Sure. In areas of Brazil, the Amazon region, the internet connectivity is covered by satellite connection, and this research is being funded by private companies around and plan to develop technologies for those really remote areas like the Amazon region, like in the countryside of countryside of other places in Brazil, not near big cities like São Paulo or Rio de Janeiro, but really far away from the urban areas.
Well, yes, as you pointed out, private companies are the ones that are investing more financial resources into providing connectivity to the rural parts of the world. Like Facebook is using balloons to provide internet connectivity in the rural areas, or Starlink itself, or OneWeb is another company that's targeting this objective. I would say that in order to get the revenue out of this, it's more important for them to provide connectivity where there is a lot of population. So where the issue is not because the area is rural, but because there is no terrestrial fixed infrastructure yet. For the rural areas instead, I'm not sure, we need to think about a new business model for telecom vendors to spend money to deploy some nodes to provide connectivity in those areas, because they will not benefit and get revenues out of there simply because there is not enough people to support and benefit from this connectivity. So satellites are a very good example of this, because satellites, they orbit. So eventually they can provide coverage connectivity also in a certain area, in a certain rural area. So they can be deployed to provide connectivity in the urban areas, or where there will be more people benefiting from the services. But when they will orbit, given that they are already deployed, they can also be used to provide connectivity to the other rural areas. So in this case, I can say that probably satellites will be the most right technology to provide connectivity to these areas, and this is what this is also in the direction of what Starlink is supporting.
Thank you, Professor Marco.
Thank you.
Let me see if we have more questions in the chat. For the moment, not. Professor Marco, I will make a final question for you. Situation are not.
We're losing you, Leonardo, a little bit. You back with us? Okay, let me read your question, Marco. So Albert is asking, can you please provide comments on the approaches focused on separation of control and data in the RF channel? in particular with regards to the power consumption and the OPEX reduction? I can't do better than that.
Okay, thanks for the question. So if I understand properly, you are asking clarifications about the division of the control and the data plane in the channel, like the services that can be provided by SDN and how power consumption and operational expenses can be reduced. Let me say that what we can have when we replace, when we split the CU and the data plane and the control plane, is that we can make and optimize them individually. And this is what we need to have when we replace the hardware with the software. So from one point of view, we don't need anymore a physical place where we need to install the hardware, because we can leave it existing with the software. So this is one part where we can provide better reduction of the costs for the management, for the deployment of the infrastructure that is not needed anymore. And this also goes well with the concept of cell-less architecture that I have explained before. And another is in terms of power consumption for the management. As I said, if we operate, for example, in terahertz, we need to support hardware devices that can operate at very large bandwidth. And this is very expensive, both to design and then to manage. If we are able to reduce and replace the hardware with a software-like product that can operate with very high frequencies, like at terahertz, then we can reduce the energy that is required to power up these devices. So this is the main approach. And when we split the control plane and the user plane, then we can provide better optimization in the control plane by leveraging, for example, the sub-6 gigahertz frequencies that are stable, that are very robust, whose propagation characteristics are very reliable, and we can use them for the channel estimation part of the network, or to exchange the control signals that require to be very robust and reliable, because they are the most important part of the network. And then in the data plane only, we operate through higher frequency spectra, like at millimeter waves or at terahertz, where we actually need to benefit from the very large throughput and very low latency that these technologies can provide. And this can only be done if we split and we separate the control and data plane together in the RF domain. I hope this answers your question.
Albert, you have raised hand. If you wish, you can unmute yourself and speak, of course.
Thank you. Thank you very much for its nice explanation, and it was perhaps focused more on SDN part. In one of the recent courses, online courses, I saw an approach which I thought fairly interesting, and which is yet another alternative to address the same important goals as you have highlighted, reaching further, making it more relevant to rural areas, reducing power consumption, and thus reducing the operational costs, OPEX. The approach is in separation of the data and control sent over the RF channel, so over the spectrum. So basically then there would be, say, only one base station per large area, which would be transmitting synchronization signals, and multiple small base stations which would be providing the data to the users. And this approach, according to those papers, is supposed to significantly reduce the power consumption in the network, because now the network doesn't need to transmit synchronization signals from every base station, even when they are in idle mode. So I thought maybe this could be also a good alternative.
Okay.
Thank you.
Thank you for suggesting this.
Marcus, seems like that we lost Leonardo. His connection is intermittent. So if you didn't catch, everybody, Leonardo was joining us from Brazil. So that's a kind of very interesting way to connect us all in the same session. So I don't see any more questions. So I suppose we can also wrap it up slowly. If you have any final, message for the audience, you can do it right now. And
well, the final maybe message I can deliver is that we don't need to leave alone 5G. The innovations in 5G will still need efforts and research efforts to optimize them and make them fully ready for the market and for the commercial rollout. So what I may suggest is to look through what 6G would look like, but always keeping an eye on 5G technologies and how and whether they can be improved to actually optimize the network performance. That still need the performance still needs a lot of optimization in this context. So I feel like saying this disclaimer because I don't want to give the wrong impression that we are done with 5G and we can go into 6G already.
well, thank you, Marco. It was really a great talk. Very interesting. Today's 5G is the hot topic, definitely. We can hear a lot about it, perhaps more than we would like to in some cases. But it is really nice to see that we are also looking toward the future. And as part for that, thank you for having this talk on behalf of Connecting Experts as well. And Leonardo, thank you for moderating this part. If you are here, you can also close the session yourself.
Okay, thank you very much then, and thanks for attending. Bye-bye.
Very much.